All right, so now let's start the day. And my talk is on SD-RAN. So I will be trying to go over the transition that the RAN ecosystem is going through disaggregation, openness, and programmatic controllability. So our journey with this disaggregation, openness, and SDNization of the RAN starts with an architecture that actually has none of these features. Until recently, all radio access networks were very tightly integrated with vendor-specific interfaces. At each tower, we had the RF units and antennas mounted with a baseband unit at the tower base where the RAN protocol stack ran. Even though various organizations, such as Small Cell Forum, had some of the open interface specifications, for the majority of cases, the interface between these components were vendor-specific. Further, each vendor had its own portal to configure, control, monitor, and log their own equipment. And this portal had vendor-specific interfaces to operators' OSS BSS, as well as regional SON control platforms. Now, having established very briefly our starting point, let us now discuss RAN disaggregation. At a high level, the base stations are responsible from two fundamental tasks: conducting packet and signal processing to transform IP packets to physical layer packets and vice versa, and also to control the mobile link, which is inherently a broadcast link shared by many devices over a fast time-varying condition. The base station uses a protocol stack to deliver on these tasks. Here you see the packet and signal processing components depicted in blue and the mobile link control components depicted in red. Then in the ORAN consistent architecture, the disaggregation we're talking about will take place in two dimensions. First is the horizontal disaggregation, which will effectively disaggregate this stack into three components and realize them in distinct locations: radio units or RUs at antenna sites, distributed units or DUs at cell sites, and CUs or the central units as virtualized workloads. The second phase of the disaggregation is a vertical one, where we will disaggregate the CU into its user plane and control plane components. Here, the CUU will process and forward user traffic. The CUC will serve two purposes again: process and forward mobile control related traffic back and forth the mobile core, and oversee near real-time mobile link control using radio resource management functions. The last phase of the disaggregation is bringing SDN-based programmable control to the RAN. This will introduce a near real-time RAN intelligent controller, or RIC, to the architecture as the SDN-based RAN controller. Running on the near real-time RIC platform, we will have numerous RAN control applications called XApps by ORAN. In a true SDN fashion, this will allow us to potentially further disaggregate the CU, lift the RRM functions from it, and realize them as control applications. Once we have the near real-time RIC platform, this becomes a unified place for SON applications and policy-driven applications as well. And some of the RAN control will also take place in non-real time. So a non-real-time RIC will also be part of this architecture. Operators' services management and orchestration platform will push operators' policies and related configuration specifics, which will then become constraints for the operation of the network. So summing up all of these components gives us an overall view of the disaggregated ORAN architecture. The disaggregated RAN enables us to efficiently pool resources. The RUs will provide coverage and capacity for the customers. Multiple RUs will be pooled by the DUs, and multiple DUs will be pooled by the CUs. The near real-time RIC will oversee a geography and control all disaggregated RAN nodes, called actually generically E2 nodes in the ORAN architecture. Since XApps will be running on the near real-time RIC, they will control this geography as well, but more on this later. Latency has always been critically important for proper operation of mobile networks, but with 5G, its importance is increasing. With LTE Release 14, the radio latency has already been reduced to 9 milliseconds. With the first phase of 5G, we expect this to go down to about 4 milliseconds. The later phases of 5G will bring further gains in performance, further reducing this to sub-milliseconds to enable ultra-reliable low-latency communications. However, the radio latency is only a small component of the end-to-end latency equation. Transport from the mobile network to where the application we're wanting to utilize is the dominant factor today. For example, transmission between two hyperscaler data farms can take up to 350 milliseconds. So this really necessitates a distributed cloud realization of the 5G mobile network for it to realize actually its far-reaching goals of various business verticals. So the exact locations of the different clouds, the far edge, the central clouds, will all depend on what the operator wishes to achieve with 5G, both in terms of business verticals and also in terms of the ORAN architecture. For example, if time-sensitive networking is to be employed, the front haul between the RU and the DU needs to experience no more than 100 microseconds of RTT latency. So with a fiber connection, this translates to a maximum distance of about 10 kilometers between each RU and the CU. Now, if the operator wishes to utilize a near real-time RIC platform, mainly for policy-based applications, as well as some SON control, it may be possible to run it in the central cloud, provided that the data farm you're running it on is regional. But if the operator's ambitions are greater and it wants to assert more control, specifically more delay-sensitive control on the RAN, with the near real-time RIC, then its correct placement will be in the same hierarchy as the CU. Similarly, the RRC-based radio resource management algorithms require end-to-end latencies of no more than 50 milliseconds. If we want the fiber transport contribution to the delay budget to be no more than 2–3%, then the component on which these algorithms run, which is CU and now the near real-time RIC, should not be any more than about 100 kilometers away from any of the end users moving around the network. So now, let us go over the near real-time RIC operation to understand what services it needs to provide as a platform. Imagine this RAN network state. We have a number of end devices, some of which are mobile. They're being serviced by geographically distributed RUs that are pooled by DUs, which are then pooled by the user plane, control plane separated CUs. Now, each of these devices has certain attributes that may be useful while conducting computations to make RAN control decisions. For example, the capabilities of the end devices and the E2 nodes, namely which frequencies they support, how many antennas they have, how much power the E2 nodes currently transmit, where they are, how many end devices they can support, etc. In addition to all of this, though, the time-varying channel qualities of the end device that the end devices observe from the active RU, as well as the quality metrics from all neighboring RUs as potential next hops. And these could be on a per RU antenna level for efficient MIMO utilization, would be of great value as well, especially if the near real-time rig is hosting some RRM XApps. So all of this network state information is to be collected and stored by the near real-time rig. Then we need a southbound. We call this the E2 termination, as well as a data store to maintain this network graph. Clearly, we would need a messaging infrastructure internal to the near real-time rig to pass information between these rig-specific internal services. We will also need to gather and maintain policy information from the operator's service management and orchestration, as well as some instructions from the non-real-time rig. This means we need terminations for the corresponding interfaces. Now imagine we have a number of XApps. Based on operators' desires and XApp capabilities, a given XApp may interact with only a subset of the E2 nodes via the E2 termination. A subscription management service will provide the means for the XApp to route relevant messages back and forth between itself and the E2 nodes it can interface with. And these XApp decisions may also actually conflict with one another. Then we need a conflict mitigation mechanism. We also need to make sure that no XApp ever goes rogue on us. So that means we need a security service as well. And last but not least, the near real-time rig conducting critically important control operations will need to be highly available. This means the platform should be able to operate in a multi-cluster environment. XApps may conduct various types of operations. To conduct these operations, based on what we just discussed, they need to directly interface with all of the termination points, E2, A1, and O1, as well as the shared data layer, where the network state is maintained, and the subscription management service. It is essential that we unambiguously define open APIs to exchange information with these near real-time rig services. These APIs should clearly specify what types of information flows we can conduct, what the corresponding data models need to be, and the corresponding transport protocols. This is critically important to ensure that we allow for any third-party XApp to interface with any E2 node that it is capable of interfacing, as long as the operator wants it. This will potentially fuel innovation in the RAN control, and we will move towards more spectrally efficient operation while maintaining service, use case, and user-specific quality of experience requirements. Open APIs should also enable the XApp developers to easily develop solutions in the programming language of their choice and allow for near real-time rig platform portability of these applications. The Open API specification work has recently started in ORAN, in Working Group 3. And as ONF, we are actively contributing to it. This brings us to the SD-RAN project. As part of this project, we have been developing an ONOS-based open source near real-time rig platform. You probably know a first generation implementation of ONOS has been in use for over 5 years now. It currently controls Comcast's trellis-based fabric rollout in a number of geographies in the US, serving hundreds of thousands of live customers. The ONOS-based near real-time rig platform derives the efforts to develop the next generation of ONOS based on a microservices architecture. We call this micro-ONOS. Just like its classical counterpart, micro-ONF near real-time RIG clearly separates the southbound termination, the core, and the northbound termination elements to delineate the roles and responsibilities and to encapsulate the nuances and complexity of the respective code areas. The micro-ONF RIG enables a multi-cluster operation for high availability and scalability. The southbound interface of the micro-ONF near real-time RIG is the ORAN specified E2 interface. All of the services that make up micro-ONF near real-time RIG are written in Go and leverage the widely used and adopted cloud interfaces of protobufs and gRPC for its internal inter-service communication. micro-ONF near real-time RIG uses state persistence and distribution strategies appropriate for the RAN-specific time-varying nature of the network state. The time-varying network state is maintained in two categories in our case, topology and telemetry. The distinction here really lies in the time scale in which this information varies. For static and slowly changing components, we use a distributed key value store. And for us, it is our own atomics in this case. Atomics provides us with the primitives for scalability and high availability. For fast time-varying components or information components, a time series database is utilized. And we also have an interim open API interface that we are leveraging to contribute to ORAN as we speak, on which we run two simple skeletal XApps, a handover application, as well as a mobility load balancing application. And since there are no ORAN architecture consistent E2 node products in the market yet, we have also developed an emulation platform on which we conduct the development, testing, and bug fixes. The user interface of the emulation platform is shown here. This user interface is linked to Google Maps. On a specific geography, we drop multi-sector E2 nodes, as well as high mobility end users at any scale we want. Then as users roam around, the network state information is collected by the near real-time RIG and maintained in its distributed data store. For XApps, in our case, handover and mobility load balancing applications, they leverage this information and assert control to this geography. So we observe in our user interface, devices being handed over between E2 nodes and the transmit power levels of the individual E2 nodes changing over time. The micro-ONF-based near real-time RIG platform is cloud native. It uses the widely adopted CNCF platforms such as Kubernetes, Helm, Prometheus, and Grafana. Here you see its Grafana dashboard. The dashboard gives us a detailed monitoring capability in a time series format. As such, we see for each XApp performance metrics, their deviation, their averages, etc. We also see the frequency of control decisions here. Leveraging any part of this data, we can also readily use Prometheus to set up alerts so that we can act quickly whenever, or even better, right before an incident occurs. ONF RIG is being designed with scalability and high availability in mind. So here you see our initial performance results for the centralized handover operation. When high availability is not a concern, you see that we achieve very good end-to-end latency numbers. For a geography spanning 100,000 users and users moving with really high speeds, resulting in around 300 handovers per second, we observed that we achieve latencies under 5 milliseconds 99% of the time. When we enable a multi-cluster operation for high availability and further scalability, we need to distribute the network state across these clusters. So naturally, this steals away some of our performance. But with our ongoing further optimizations, we now report that even in an HA deployment, the latency performance is 10 milliseconds, 99% of the time, with the worst performing handover procedure over a very long period of time experiencing under 58 milliseconds. And this pretty much actually is in line with a typical handover round trip delay requirement of today's networks. So the journey towards disaggregated, virtualized, open, and SDNized RAN started in two parallel trusts, the XRAN Forum in the US and the CRAN Alliance in China. In June 2018, the ORAN Alliance was launched by merging these two initiatives. ORAN's objectives are actually very ambitious. It is to promote the adoption of open interfaces and infrastructure to allow multi-vendor deployments, achieve faster time to market and expedite innovation, decrease the total cost of ownership through increased competition, white boxes, and open source components. Rapid and broad industry promotion and adoption of open standards, interfaces, APIs, as well as RAN programmability and service optimization, leveraging AI and ML techniques. ONF has become an ORAN member in January, and TIP signed a collaboration agreement with ORAN in February of this year. So at ONF, we are developing, as I mentioned, our highly available latency sensitive and scalable near real-time RIC, and the ecosystem is leveraging that platform to develop XApps for some innovative network control. And at TIP, open hardware specifications are being pursued. And the ORAN software community brings in both open and proprietary components for all aspects of the ORAN architecture that I showed earlier. So these initiatives share the common ORAN goal. Moreover, towards that goal, they have started interacting and collaborating. There is now some code exchange between them, sharing of experiences. But even more importantly, there is now collaboration towards ORAN working group contributions, feeding all of this experience back for specifications. Our work on the SD-RAN project is ongoing in collaboration and interaction with our ONF partners and members. So even though SD-RAN was very recently launched, as you can see, we have already a very large number of operators and vendors who are part of this ecosystem. And the goal is to bring in intelligence to the disaggregated ORAN architecture. So some key takeaways before I hand over to Tarek. So the future of RAN is disaggregated, it is open, and it is programmatically intelligent. And it is also virtualized. Disaggregation across the geography will depend on technology and business use cases. So we will either actually co-locate all of the disaggregated components all in one data center or distributed around as the use case demands it. An open RAN will enable multi-vendor deployments in both dimensions of the disaggregation. So both in the RU/DU CU front, but also on the CU near real-time RIC platform and XApps dimension. The near real-time RIC is a critically important component of the RAN. It needs to be performant, scalable, and highly available. And here at ONF, our SD-RAN project is developing a near real-time RIC platform that is micro-ONOS based. Our mission is to really bring in true SDNization to the RAN in a performant, scalable, and highly available manner. And we expect a wide range of third-party XApps to expedite innovation towards more efficient means of RAN control. And last but not least, careful specification of open APIs will definitely enable the ease of XApp development and inter-near real-time RIC platform portability. So with that, I conclude my talk. Thank you.